In grade 10, you learned that to find the solution to a linear system, you had to find the point of intersection between two linear equations. Now, in grade 11, we talk about linear quadratic systems. So a linear quadratic system is a system of equations where one of the equations is linear and the other equation is quadratic. But by looking at the two equations together as a system, again, similar to linear systems in grade 10, if we want to find the solution to a linear quadratic system, that will involve finding the point or points of intersection between the linear function and the quadratic function. Okay, so here's the kind of question that you might see. Determine the point or points, you see the S's in brackets there, of intersection of these two functions. Y is equal to negative x squared plus 2x plus 4, and x plus y is equal to 4. So we see that the first one here is indeed a quadratic function, and the second equation does represent a linear function. And the reason this question says point or points is because it's possible for a linear quadratic system to have more than one solution or more than one point of intersection. Right? Picture for a moment a parabola. Right? And if we look at how many ways a line can intersect that parabola, we can draw a line that intersects this parabola in two locations. And so that line and that quadratic function would have 2 points of intersection or two solutions to the system. We could draw a line that has 1 point of intersection, so it just touches the parabola at one location. Okay? Or we could draw a line that has no points of intersection. Okay? So here's an example of a line that would not intersect the parabola at all. Okay? So it's possible for a linear quadratic system to have no solution. It's possible for it to have one solution, and it's also possible for a linear quadratic system to have two solutions. All right, so let's take a look at this question. Now, in grade 10, you looked at solving linear systems in 3 different ways. You did it graphically, using substitution, and using elimination. Now, with linear quadratic systems, the method that we usually want to focus on is using substitution. It becomes a little bit trickier to use elimination due to the fact that the quadratic equation has an x squared in it, and the linear equation does not have an x squared term. And we know that using graphing as a method to solve for points of intersection is only really good when our points of intersection end up being integer values for the x and y coordinate. So it's not always reliable depending on what our points of intersection end up being. Okay? So using the method of substitution, I'm going to start by calling the quadratic equation, equation 1. Now, it doesn't really matter which one's equation 1. This just makes it easier for us to refer to the two different equations as we work through the problem. And the linear equation as equation number 2. Okay. Now, the first step for substitution is always to make sure that one of the equations is solved or rearranged for one of the variables. And equation 1 is already solved for y, so we don't need to worry about that. Okay. Now, since we know that y is equal to this expression that's on the right-hand side of that equation, we can use that expression in place of y in the second equation. So what we're going to do, this is the first substitution step, we're going to substitute negative x squared plus 2x plus 4 in place of y in equation 2. Okay? And so we've got x plus, and then in place of y, we're going to substitute negative x squared plus 2x plus 4, and then equals 4. Okay. Now we have an equation that we can solve for x because by making that substitution, we now only have one variable in this equation. Okay, so if I add these terms, so collect like terms, I get negative x squared plus 3x plus 4. And in order to rearrange that, I have 0 on one side, I can subtract 4 from both sides of the equation. Okay. So simplified, I get negative x squared plus 3x is equal to 0. Okay. Well, this equation can be factored, and so on the left-hand side, I can factor out negative x, and I'm left with x minus 3 equal to 0. Okay. Continuing, so solving this equation, I've got two possibilities. Either x is equal to 0 or x minus 3 equals 0. And so I get either x equals 0 or x equals positive 3. Okay. So there will be 2 points of intersection to this particular linear quadratic system. The first point of intersection happens when x equals 0, and the second point of intersection happens when x equals 3. And so from here, we need to use each of these different x values in order to substitute into one of the equations to solve for the corresponding y values. Okay, so we got two different x values. The first x value we got was x equals 0. And if x equals 0, then, well, let's use the second equation to work with here because it's the linear equation. It's a little bit easier to work with. So if x equals 0, we get 0 plus y is equal to 4, which means that y has to be 4. This gives us the coordinates 0, 4. 0 is the x coordinate, 4 is the y coordinate that we just solved for. And so we know 0, 4 is one of the points of intersection between this quadratic function and this linear function. Okay. The other x value that we got was x equals 3. So if x is equal to 3, again, let's use the linear function. We get 3 plus y is equal to 4, which if we rearrange the equation, we get y equals 1. And so that gives us the coordinates 3, 1. So what we've just done is solved for the 2 points of intersection between this quadratic function and this linear function. The 2 points of intersection are 0, 4 and 3, 1. For this particular question, we don't actually need to find the points of intersection. All we want to know is how many solutions or how many points of intersection are there. Okay, so the first step is we want to make sure that one of the equations is solved for one of the variables. And equation 1 in this case is already rearranged for y. And so we can take that expression for y, 6x minus 4, and we're going to substitute that expression, so 6x minus 4, in place of y in equation 2. Okay? So we get 5x squared plus 4x equals 1 plus, and then in place of y, we replace 6x minus 4. Okay, we now have an equation where there's only one unknown variable, the x value, and so we can rearrange and solve for that. So if I rearrange so that I have 0 on the right-hand side, I get 5x squared plus 4x minus 6x, so negative 2x, and then negative 1 plus 4, so positive 3 equals 0. So now we have a quadratic equation, so we want to look at possibly factoring this. Now taking a close look at the left-hand side of this equation, it's not factorable. Okay, so you can go through a quick check there to check for your different types of factoring. It's not factorable. There's no common factor. Then we take a look at using quadratic formula. However, you might want to keep in mind the discriminant here, because if we apply what we know about the discriminant, that will tell us how many solutions this linear quadratic system has. Okay, so if we use full quadratic formula, that will solve for the solutions. But if we just use the discriminant, we can figure out how many solutions there will be. Okay, so the discriminant, as a reminder, b squared minus 4ac. And so we want to list out the a, b, and c values. A is 5, b is negative 2, and c is 3. And we substitute them into the discriminant. So we get negative 2 squared minus 4 times 5 times 3. And so we get 4 minus 20 times 3 is 60. which is negative 56. Okay. Since the discriminant is a negative value, that tells us that there are no solutions to this linear quadratic system. Okay? So because there are no solutions to this quadratic equation, and that happened after we did the substitution here, that means there's no solution to this linear quadratic system. So because of this discriminant being negative, so since b squared minus 4ac is negative, there are no solutions for this linear quadratic system.